Hello students, today's learning objective is about systems that are having congruent melting point. Already I have started the phase rule in the previous sessions. Phase rule for one component system, phase rule for two component systems was discussed. And in this category, we are going to say about two component system which are having congruent melting points. Now, the systems that are having congruent melting points. The phase rule it is to study the behavior of the heterogeneous systems. Phase rule was proposed by William Gibbs in 1874. Phase rule helps in studying the heterogeneous equilibrium systems with two or more systems that are in equilibrium. Phase is denoted by P. Phase is a part of a system which is homogeneous, physically distinct by boundary surface, and it is mechanically separable from other homogeneous parts of the system. Mixture of two or more gases, you take example, mixture of two or more gases, or mixture of two or more miscible liquids that are homogeneous. So the phase will be 1. For homogeneous, it is 1. Two immiscible liquids will take two solids or solid plus gas. A solid plus gas or solid plus liquid, liquid plus gas will take. All these, they're having example water plus phenol, water plus benzene. Water plus benzene. So for these systems, their phases are 2. The phases are 2. Next, we'll take calcium carbonate when it is heated. When it is heated, we have CaO and carbon dioxide. The two solid phases and one gaseous phase. Phases are 3. Calcium carbonate is solid, calcium oxide is solid, carbon dioxide is gas. So the components, the phases are 3. One is solid, one is solution, one is gas. Allotropes of sulfur with different structures. You have rhombic sulfur, you have monoclinic sulfur. So that the phases are 2. Similarly, ice, water, vapor, the phases are 3. Okay, I think you have clearly understood about a phase. Part of a system which is homogeneous, physically distinct by boundary. And this is mechanically separable. Okay, that is called a phase. Now, we'll see what is a component. Component, it is denoted by C. Number of components in a system is the smallest number of independently variable constituents by means of which the composition of every possible phase in the system can be expressed with formula. That is called component. Water, it has 3 phases: ice, water, water vapor; solid, liquid, liquid vapor. So the component is 1, the phases are 3. So I think you have understood the clear example of a example for a component. Number of components is the smallest number of independently variable constituents by means of which composition of every possible phase in the system can be expressed with a chemical formula. Now, degrees of freedom, the number of degrees of a system is number of factors, temperature, pressure, concentration of components that can be varied without altering the number of phases is degrees of freedom. Okay? So you have understood what is a phase, what is a component, and what is number of degrees of freedom. So represented by P, C, and F. What is phase rule? The sum of number of degrees of freedom F and number of phases P exceeds number of components by 2. It's called Gibbs phase rule. F plus P is equal to C plus 2. So I'm giving you the introduction before starting the system of congruent melting point systems. Next, there you are having one component system. Now, later on, we are having reduced phase rule or condensed phase rule. Reduced phase rule, condensed phase rule. The gaseous system, which involves large change of volume affected by pressure. So the system is having only solid and liquid phases and are not considerably affected by change of pressure. Such a solid liquid systems with gas phase is absent is called condensed phase. Where there is no gas phase is condensed phase system. It is a condensed system. So the degrees of freedom is reduced by 1. There is no gas phase. Degrees of freedom is reduced by 1. So vapor pressure of the solid is very less. Therefore, it is getting reduced by 1. So you are having the reduced phase rule. What is the reduced phase rule? F prime is equal to C minus P plus 1. F prime. F is the number of degrees of freedom. The variables for two component solid liquid systems are temperature, composition. The phase diagram for such systems consists of temperature, concentration graphs. Okay, so now we are going to discuss only about the solid solutions. There is no gas phase. Condensed phase rule is applied here. When two solids are melted together and liquid cooled, sometimes the substances are decomposed together. So this is usually the case where the substances are isomorphous. The solids thus deposited is called solid solution. A solid solution is defined as homogeneous mixture of two or more crystalline solids that are varying in the proportions. Now, the solid liquid equilibria. Solid liquid equilibria are divided into different types depending upon the miscibility of the two compounds. If two compounds are completely miscible and non-reactive to each other, and the next one is two components are partially miscible, but they react, and the two components which are immiscible. These are the three types of the solid liquid equilibria. Now, based on the nature of the solid phase that separates out during cooling the system, this is divided into three types. Yeah, now comes our actual concept of systems that is having congruent melting systems. See, and the nature of the solid phases that are getting separated out during cooling the system are divided into three types. Two components do not form any compound, and on solidification, they simplify, form an intimate mixture called eutectic mixture. The previous session was about this two component system, eutectic mixture. Now, the example is lead silver system. The second system is two components combine to form compound with congruent melting point. The two component system form a solid compound called intermetallic compound. It is stable up to its melting point. Example is zinc magnesium system. I am repeating, the two component system combine to form compound with congruent melting point. With congruent melting point. Two components form solid compound known as intermetallic compound. Reaction, both of them react and form intermetallic compound. And this is stable to its melting point. Example is magnesium zinc system. A binary system. The binary system possesses the congruent melting point. And when this melts, it melts at sharp temperature. It gives liquid of same composition as that of solid. So the components of binary mixture at certain stage enter into chemical composition, form one or more compounds, intermetallic compounds, in stoichiometric proportions. Intermetallic compound is formed in stoichiometric proportions. These compounds melt sharply at a constant temperature into a liquid having the same composition as that of solid. So the components of binary mixture at certain stage they undergo, they react chemical composition and form intermetallic compounds in the stoichiometric proportions. These compounds melt sharply at constant temperature into liquid and they have the same composition as that of solid. Although they melt sharply, the composition will be the same as that of solid. So the temperature at which such compound melts is called congruent melting point. Intermetallic compound is formed and the composition is the same. They melt sharply at constant temperature. The whole liquid mixture, intermetallic compound, whole compound mixture, melt sharply at constant temperature into liquid. And they have same composition as that of solid. So the temperature at which compound melts is called congruent melting point. And similar examples as that are zinc and magnesium system, mercury thallium system, gold tin system, ferric chloride and water system. All these are congruent melting point systems. Now you have understood the example of the congruent melting points. So the binary mixture, when you mix the binary mixture, they at a certain stage they enter into chemical combination, form one or more compounds. They form one or more compounds, that is intermetallic compound is formed. In stoichiometric proportions they form. And thereby they melt at constant temperature with no change of composition as that of solid. The composition is same as that of solid. That is called congruent melting point system. Now, we'll have a look onto the zinc magnesium system. Now, in the zinc magnesium system, it is the two component system, possess congruent melting points. The phase diagram of the zinc magnesium system is shown in the below diagram. In this system, the two compounds are zinc magnesium. It melts at 419 degrees centigrade and 650 degrees centigrade respectively. And these are represented at points A and B in the phase diagram of the system. They're represented in the phase diagram. Both the metals enter into chemical composition, form intermetallic compound magnesium Zn2, MgZn2. Zn2. And the melting, they melt at 590 degrees centigrade. This is the congruent melting point. This intermetallic compound is formed and it melts at 590 degrees centigrade. The composition will not change. It is same as that of the solid. Yeah. This solid melts into liquid, but composition is same. The melting point is 590 degrees. This is called congruent melting system. And the liquid of the same composition you get as a tool. Hence, 590 degrees is a congruent melting point of the system. In the reduced form, the system has 4 phases. A compound which melts sharply at constant temperature into liquid at the same composition as solid is said to have the congruent melting point. Magnesium zinc system. Two compounds combine to form the solid compound intermetallic compound with congruent melting point. And it is stable till its temperature, 590 degrees. Its melting point. Okay. The compound which melts sharply at constant temperature into liquid of same composition is called compound with congruent melting point. Now, it is typically two component system, involves the formation of the intermetallic compound MgZn2. Here in this system, we are having 4 phases. Solid magnesium. Where is solid? Here. Solid magnesium. Next, solid zinc. Solid MgZn2. Solid here, MgZn2. Next, mixture of Mg and Zn. Mixture of Mg and zinc. The molten mixture of Mg and Zn. It is shown in the figure. This diagram consists of curves, areas, 2 eutectic points, C here, and E are the 2 eutectic points, and one congruent melting point, that is D. This complete diagram, you can see we are having curves, we are having areas, solid magnesium, solid zinc, solid MgZn2, molten mixture of Mg and Zn2. And along with this 2 eutectic points C, E. And one congruent melting point, that is D. Now we'll have, I'm going to explain. We have to apply the reduced phase rule for this system. F prime is equal to C minus B plus 1. Actually, it is 2. There is no gaseous phase, so degrees of freedom is reduced by 1 plus 1. Now we'll see at point E, at point D, non-variant system. Incongruent melting points in this. This is the congruent melting point D. At this D, it is non-variant system. At point D, it is non-variant system. Why at point D it is non-variant system? Now we'll see about the point C, point D. At point D, it is congruent melting point. At point D, composition of MgZn2 solid, it is equal to composition of the solution. The temperature corresponds to this point, that is congruent point. At this point, 2 phases are in equilibrium. MgZn2 is in equilibrium with liquid. Yeah, this liquid and MgZn2, both of them are in equilibrium. Okay, therefore here the phases are two, solid phase and the liquid phase. Composition is only one, MgZn2, in equilibrium with MgZn2 solution. So C is 1, P is 2. Therefore, C is 1, P is 2. 1 minus 2 plus 1. Okay, 1 minus 2 plus 1. So 2 minus 2 0. So at this point, it is 0, invariant system. F is 0, invariant system. Now, at point E, we'll see. Point E, point C. Later on, curves and areas will discuss. Point E is eutectic point. Point E, point C, eutectic point. So point E represents eutectic point of the system at temperature 345 degrees centigrade. Next, this is the least melting point of MgZn2 system. Here you can see three phases existing together in the equilibrium. At point E is the solid magnesium and solid MgZn2 and liquid MgZn2. So C, the composition is 2. MgZn2 is one composition, Mg is one composition. The phases are three. Here solid, liquid, and again solid. So 2 minus 3 plus 1. 2 minus 3 plus 1. 2 is the composition. P is 3 phases plus 1. It is equal to 0. So the system is non-variant system. So 2 minus 3 plus 1. It's equal to 0. The system is non-variant. Next, point C will say eutectic point C. Yeah, this one. In eutectic point C, it represents the eutectic point at 380 degrees, the 380 degrees here. It is the least melting point of Zn and MgZn2. E is the least melting point of Mg and MgZn2. Point C is least melting point of Zn and MgZn2 system. Now at this point, the three phases are solid Zn, solid MgZn2, liquid MgZn2. All these exist together in equilibrium. So C is 2, P is 3. F prime is equal to C minus P plus 1. This is equal to 2 minus 3 plus 1. It is equal to 0. It is equal to 0. Now the areas. So at point C, it is non-variant system. At point C, it is non-variant system. So at point D and point E, so point E, Zns is in equilibrium. Yeah, this is the point E. Zinc solid is in equilibrium with MgZn2, which is in equilibrium with solution. So P is equal to 3, C is equal to 2, F is equal to C minus P plus 1. F is equal to 2 minus 3 plus 1. F is equal to 0. System is invariant. Now, as we have discussed for C, three phases are in equilibrium for the C. Mg is in equilibrium with Yeah, magnesium and zinc. Here, magnesium is in equilibrium, and here Zn is in equilibrium. Okay, so at point E, Mg is equilibrium with MgZn2, and which is equilibrium with solution for at point E. Now at point C, Zn, Zn is in equilibrium with MgZn2, which is in equilibrium with solution. At point E, Mg is in equilibrium with MgZn2 and liquid. At point E, these three are in equilibrium. Okay, magnesium, zinc, and solution. So phases are 3, C components are 2, and F is equal to C minus P plus 1, F is equal to 2 minus 3 plus 1, F is equal to 0. So system is invariant at point E. Now similarly at point C, zinc is in equilibrium with, zinc solid is in equilibrium with magnesium zinc, which is in equilibrium with solution. So P is 3, C is 2. F is equal to C minus P plus 1. So F is equal to 2 minus 3 plus 1. It is equal to 0, invariant. 0, it is invariant. Now let us have a look onto the curves. Okay, here are the curves. So we'll see the areas, then we'll go on for the curves. Now coming to the areas, the phase diagram of the zinc magnesium system consists of many areas. It is consisting of many areas. The phase diagram, the many areas, the curve B, C, D, E, A. B, C, D, E, A. B, C, D, E, A. It is complete single phase. B, C, D, E, A. This complete one is single phase. And on this one, the area it is complete liquid melt. You're having zinc and magnesium. C is 2, P is 1. Now apply the formula. F prime is equal to C minus P plus 1. This is equal to 2 minus 1 plus 1. It is equal to 2. So only for that area it is bivariant system. Only for this above area it is bivariant system. Now most of the areas of zinc magnesium system consists of two phases. As I've told you, they are having two areas, two phases, and completely they constitute for univariant systems. So phases are two here. You take this complete area, it is only one, and you get bivariant system. Now for this area, this area, and this area, everywhere you take, you get two phases. You get two phases for all the areas. And the composition is 2. C is 2, P is 2. For all the areas, C is 2 and P is 2. Okay, so for the other areas of the zinc magnesium system, the P, they have two phases, all the areas, and the composition is also 2. So for this area, all these areas, you're having P is 2 and C is 2. Therefore, F prime is equal to C minus P plus 1. 2 minus 2 plus 1, it is 1. So the system, all the areas you get by here, you get univariant system. I'm repeating, for this complete above area, you get bivariant system. C is 1, P is 1. You get bivariant only for this melt. B, C, D, E, A. Now coming to the remaining remaining areas or remaining all areas you have the same. C is 2, P is 2, and F you get it as 1. So all the areas you get as the univariate systems. Okay. Now for the points C, you get non-variant. Point D also, you get non-variant. Invariant systems for all the points C, D, E. For all the points, you get invariant systems. C, eutectic points, E, eutectic point, D, congruent melting point. You get invariant systems. For this above area, you are getting bivariant system. You are getting bivariant system. And remaining other areas, you are getting univariant system. So I hope you are clear with the points and the areas. All points C, E, D, eutectic, congruent, melting points, invariant system. It is independent of neither temperature nor composition. Now coming to the areas, the above area it is bivariant system. It is dependent on the concentration and temperature. And remaining bottom areas, it is univariant system. It is dependent on any one concentration of the temperature. Now, let us have a look onto the areas. Areas completed. Now we'll see the curves. We'll see the curves. Curve BC, freezing curve of zinc. You are having zinc and melt. You're containing zinc and the melt is MgZn2, intermetallic compound. Phases are 2, components are 2. See curve BC, freezing curve of zinc. Curve BC. This is the curve BC, freezing curve of zinc. Curve BC is the freezing curve of zinc. You are having zinc plus melt. You are having zinc plus melt. So C is 2, P is 2. C is 2 and P is 2. C is 2, P is 2. 2 minus 2 plus 1. Univariant system. So C is 2 and P is 2. F is equal to C minus P plus 1. 2 minus 2 plus 1. 1. So for BC curve, you get univariant system. Now, the next curve we'll see curve AE, freezing curve of magnesium. Curve AE, it is the freezing curve of magnesium. You have magnesium plus melt. Curve AE, we'll see. Here, curve AE. Zinc plus melt, here it is Mg plus melt. Mg plus melt. Yeah, Mg plus melt. So here you're having Mg plus melt. Composition is 2, C is 2, and phases are 2, solid and melt. Liquid melt. So P is 2 and even C is 2. So applying the formula, F prime is equal to C minus P plus 1. C minus P plus 1, you get 2 minus 2 plus 1, that is 1. The system is univariant system. System is univariant system. Next. Yeah, it's a univariant system. You also get univariant system and this one also univariant system. Next, we'll see the next curve, curve CD. curve CD. Yeah, curve CD, you are having the intermetallic compound plus liquid melt. Intermetallic compound plus liquid melt. So composition is 2 and C is also 2. Applying the formula, F prime is equal to 2 minus 2 plus 1. It is equal to 1. Univariant system. It is univariant system. Now, curve DE will see. I've told you CD and DE. CD we are having curve CD, curve CD, Mg, Zn2 and melt. And similarly, DE is also the same. CD and DE. It is both of them curves, one and the same. You're having Mg Zn2 plus liquid melt. So the T is the congruent melting point at 590 degrees. Both the congruent melting point, this intermetallic compound solid, changes into a liquid with no change in composition. That is congruent melting point. It is 590 degrees for zinc magnesium intermetallic compound. Now at curve CD and curve DE, once if you take curve C and curve DE, yeah, we'll see here curve CD and curve DE. The C is 2, composition is 2, number of phases are 2. So 2 minus 2 plus 1, univariant system. F is equal to C minus P plus 1. F prime is equal to 2 minus 2 plus 1. It is equal to 1. So for this curves CD and curve DE, you get univariant and univariant systems. Now let us go for the curve CDE. For the curve CDE. Curve CDE. You are having the intermetallic compound plus melt. Keep the same. As CD, as DE, again CD is the same. You are having zinc melt, this one, MgZn2 melt and melt. For DE and CD, D you are having Mg. DE you are having Mg plus intermetallic. For CD you are having zinc plus intermetallic. Okay, C is 2, P is 2 and F is equal to 2 minus 2 plus 1 univariant. CD and DE same. CD you are having Zn plus MgZn2. D you are having Mg plus MgZn2. So for this complete curve you are having CDE curve you are having intermetallic compound MgZn2 plus liquid melt. MgZn2 plus liquid melt. Okay, so here the composition you have C is 2 and P is also 2. 2 minus 2 plus 1. Applying the formula, F is equal to C minus P plus 1. C is 2, P is 2, 2 minus 2 plus 1. We get univariant system. We get univariant system. Okay, and for the total curve that is liquid melt, I've told you are getting bivariant system. B, C, D, E, A. B, C, D, E, A. Complete melt, zinc you're having, everything. Everything is in the molten state. So P is 1. C is 2. Okay, so F is equal to 2 minus 1 plus 1. So 2, this one. Okay. C is equal to 2. P is equal to 1. 2 minus 1, 1. 1 plus 1. 2. Bivariant system we are getting. This is about the curves. So all the curves BC, CD, DE, AE, all these curves you are having. For all these curves we get univariate system. But for BCDEA curve, we are getting bivariant system. For points, invariant system. Eutectic points as well as for congruent melting point. Now coming to the area, so as I have discussed, area BCE, zinc plus melt. Area DCG, melt and melt. So the phases are 2. Again for BCF, phases are 2. Yeah, 2 phases, C is 2. Composition is also 2. We get P is 2, C is 2, univariate system. BCF. Similarly, DCG. BCF univariate system. BCF, this area, BCF. Zn plus liquid metal. 2 phases, 2 compositions, F is 1 univariate. Now, the next area, DCG. DCG. Under DCG, we are having MgZn2 plus melt. You are having zinc and MgZ, the same. Again, there also you are having the same. DCG also you are having same. Zinc and MgZn2 here. Even this is having same Zn plus intermetallic compound. So C is 2, F is P is 2, F is equal to 2 minus 2 plus 1, univariate system. Now area DEH. Area DEH. Yeah, BCF is completed, DCG is completed. For DEH, we'll see. You're having magnesium plus intermetallic compound. You're having magnesium plus intermetallic compound. So magnesium plus intermetallic compound. Here, area DEH. You're having magnesium containing magnesium plus intermetallic compound. It is 2. Okay. So for this DEH, intermetallic compound MgZn2 plus magnesium. You get 0, 2 phases. Phases are 2. Composition is 2. F is equal to C minus P plus 1. 2 minus 2 plus 1. Univariant system. Now for area AEI. Area AEI. You are having magnesium plus liquid melt. You are having magnesium plus liquid melt. AEI. Magnesium plus liquid melt. Composition is 2, and here along with the composition the phases are 2. 2 minus 2 plus 1. F is equal to C minus P plus 1. F is equal to C minus P plus 1. C is 2, P is 2. So 2 minus 2 plus 1. AEI you get univariant system. Area below FCG. Area below FCG. See here, F, C and G, this one. Next we'll see this area. FCG area below and HEI area below. FCG below you are having zinc plus MgZn2. 2 phases, 2 chemical compositions. Area below FCG. Zn plus MgZn2. 2 C and 2. Therefore, f is equal to c minus p plus 1. F is equal to 2 minus 2 plus 1 univariate. Area below He I also have told you, magnesium plus intermetallic compound. C is 2 and P is also 2. So 2 minus 2 plus 1, you get univariate system. As I've discussed even for the eutectic points and point D, Covalent melting point, we get phases 3 and compositions are 2. So F is equal to C minus P plus 1. C is 2, P is 3. For point C, point E, point D. C is 2, P is 3. So the formula is F is equal to C minus P plus 1. So F is equal to 2 minus 3 plus 1. So 3 minus 3 is 0. Invariant system you get. For point eutectic points C and E, you get the same. And for point D also, you get the same, C, D. So this is the way we can discuss about the compounds. This one, applying our phase rule, we are able to discuss a binary system, how it is possessing the congruent melting point, and we are studying the heterogeneous system, behavior of the heterogeneous system. So a behavior of a heterogeneous system, we are able to study heterogeneous equilibrium systems. We are able to study using the phase rule. So today's class, I hope you have understood about the congruent melting point systems. Thank you, everybody.